Okay, so we're recording. Everyone got the little message here. We'll move this out of the way. We'll keep Top Hat open for a little bit. Got out of the way. Okay, so everyone can see see everything, right? I don't have my second computer turned on because things have been going well. Okay, so we left off on Friday talking about chemical potential, right? And I want to sort of rehash this because I think it's really, really important. And it's just this thing that people perpetually misunderstand, right? So the deal with, come on, zoom out of the way. Hold on, I'm just trying. So the deal with chemical potential is it's just like any other potential. It's just like voltage or temperature, right? But it represents a distribution, the density or the intensity of chemical energy in a material, right? And that doesn't have to be uniform, right? Just like in a body, you can have a temperature gradient, right? The welders know temperature gradients really well, right? You have a hot spot, and then you've got heat that's flowing away from the fusion zone out into the body of the material, right? We can have a chemical potential gradient in the same way, right? Back in 2010, you guys focused on the idea when you talked about diffusion that species diffuses from regions of high concentration to low concentration. Well, that's not entirely true, right? It's really that things are going to diffuse from region of high chemical potential to low chemical potential, right? So we can, if we look at this Gibbs free energy curve and we look at where the intercepts are, if we take a tangent line and project it back, right, that gives us our chemical potential, right? And we see that if we're out here, if we draw a tangent line for B at this point, we can see that it's going to have a much higher chemical potential. So we come down here and we're actually, if we were have a region of lower composition out here, right? Obviously, we're lowering our Gibbs free energy by diffusing down this chemical potential gradient, right? So we want to tie everything back to thermodynamics. Why do things diffuse against a concentration gradient? Because we lower our overall system free energy, right? What is the field that's really important? It's not the composition field, it's the chemical potential field. Just like heat flows in the direction specified by our temperature field, right? And if you keep that simple picture in your head, things go a lot more smoothly, right? And it's just something that's really misunderstood, and that's just because it is not explained well at all, I don't think, in most textbooks, right? Most books don't even, if you just look at the units, right? The units are joules per mole, right? It's Gibbs free energy per mole, right? So it's a partial molar free energy, right? Okay, so forging ahead, right? We spent time talking about ideal solutions. We talk about regular solutions, right? I'm forgetting how to speak. Sound like Porky Pig. Okay, so in an ideal solution, we had a delta H of mixing that we said was equal to 0, right? For our regular solution model, we're going to assume that our enthalpy of mixing is not equal to 0, right? And that energy of mixing, if that's not 0, that means there has to be asymmetric energy interactions between components, right? So if we have a binary solution where we're mixing AA and AB together, right? For the heat of mixing to be 0, it means that the bond energies between A and B, A and A, and B and B all have to be identical. And the bond lengths have to be identical, right? Because if we have an elastic stretch, that raises the internal energy of our system, right? So the regular solution is the simplest way that we can relax this. What we're going to say is that these bond energies are not exactly equal to each other, right? There's epsilons here are our bond energies, but they're pretty dang close. They're close enough that it's not going to mess with the number or the distribution of our bonds too much, right? Right, so this is basically just what I said, right? The internal energy of our system is going to depend on the number of bonds of each type that we have, right? If we consider this in the text here, PXY is the notation that's used in the reading, is the number of bonds per mole of type, right? When I think about it normalized slightly differently and think about this in terms of a probability, right? If we take the total fraction of the solution as 1, right? And we have, this is the number of bonds per mole, but if we have 1 mole of solution, right? This is, we can just normalize by Avogadro's number and think of PXY as a probability. But in the text, they talk about it as the strict number. But either way you think about it, right? PXY is some number that tells you how likely all the different combinations are, right? Could be X equals Y or X different than Y, right? What we can do then is make a relationship for our change in enthalpy, right? Is going to be the energy of each bond type times the number of bonds that we have, right? Or this is that, I said this wrong. This epsilon here is a type of average or a deviation from the average, right? So this here is the mean. You can think of this as like a mean energy, and then this becomes like a deviation from a mean, right? How different the energy of the dissimilar bonds are to the average energy of the same type bonds, okay? So if all of these have the same bond energies, then obviously epsilon goes to 0, and our delta H mix goes to 0, and we're back to an ideal solution model, okay? So you can work out from some basic statistics, right? And the exercise is worthwhile doing once. If this were a graduate class, we'd go through it. But you can go through a fairly simple statistical analysis and calculate the number of bonds, right, of each type, right? You can see that it's going to be proportional directly to the number of types of A and the number of types of B that you have, right? Z is the number of bonds per atom in your system, right? So if this is a glass, right? Silicon dioxide, where you've got the your tetrahedral, your elements of glass are your little tetrahedrons, right? Z here would be 4. Right, if you are in a BCC lattice, right, each center atom is connected directly to the 4 corner atoms of your cube, right? But this just is a little expression that lets you know how many bonds of each type that you're going to have. Okay, so what does this mean if our epsilon deviates from 0, meaning that we have an asymmetry in our bond energies, right? So if epsilon is less than 0, then atoms are going to prefer to be surrounded or near atoms of an opposite type, right? And our number of PAB or bonds, the number of AB bonds or PAB is going to increase, right? If epsilon is much, much less than 0, right, then there's a really strong energetic preference for AB over AA and BB. And we're going to form an ordered phase if it's potentially in a metal, or if it's small enough, we'll start to get ionic character to our bonding and we'll form a ceramic lattice, right? So if we have metal ions plus, say, oxides, right, with a large electronegativity difference, we form a completely ordered phase on and form an ionic ceramic rather than a metal, right? So if our epsilon is going to be greater than 0, then our atoms prefer AA and BB rather than AB, and we're going to cluster. And if epsilon is much, much greater than 0, then we're going to have a phase separation, right? So both cases are going to indicate a departure from our uniform random solution, right? For our regular solution model, we're going to assume that our epsilon is small, right? So we're going to look at things in the limit of delta approaching 0, of our epsilon approaching 0. So that means that there's differences in energy, but we're not changing the statistics. We're not drastically changing PAB, right? And so what we're going to say is that our delta H of mixing is going to be proportional to the mole fractions of A and B, the product here, times this omega term, which is a term that contains our bond energy, right? And so the interpretation of this omega term is basically the derivative of our delta H of mixing as the concentration of B or A goes to 0, right? So the change
of that, but this, well, that's actually not factual whatsoever.
Was that a commentary on my on my statement there? But anyway, so what this is this since this has a symmetry to it, or this should be, man, I'm saying this all wrong. Okay, so the tangents on both of these sides are graphically related to omega in this way. So while it doesn't look like it, this curve in the regular solution model should be a symmetric curve, right? And that the delta H from adding a small amount of B to A is the same as adding a small amount of A to B. right? We're going to increase the number of AB bonds exactly the same, whether we, right, add a tiny amount of B to pure A or a tiny amount of A to pure B, right? Not super important, but I just wanted to point out that it's a bit of an optical illusion, or this figure isn't drawn really well. This figure is not really drawn really well in your book. Right, this should be, these tangents here, by the nature of the model, need to be the same, right? This is true for a general solution, but not strictly true this picture for the regular solution. Okay, so we have a couple cases that we need to think about for the regular solution, right? We have the delta H of mixing. We have our entropy term, right? Our entropy term always wants to encourage things to mix together, right? So we could have a enthalpy term that encourages mixing, right? In which case we have a negative. And if our enthalpy term is negative, right? We have a negative energy benefit for mixing. We're always going to have complete miscibility, right? Because no matter what we do, we can lower our free energy. Our free energy is still going to be negative by mixing, by adding more in, right? A to B. So we have solubility over the complete range, right? And obviously, as we go up in temperature, our entropy term gets more negative, right? So our Gibbs free energy of mixing is going to decrease. But if we have a positive enthalpy of mixing, right, at high temperatures, our entropy term might still be high enough to encourage everything to mix, right? That we still have a negative Gibbs free energy of mixing across the whole range, right? But as we lower the temperature, the driving force due to the entropy term for mixing decreases, right? And we could have a region in the middle where we actually have a positive Gibbs free energy of mixing. So we have a phase separation or a miscibility gap, right? The maximum amount of B that we can dissolve into A is going to be dictated by where the delta G of mixing becomes positive, right? And the same thing, the maximum amount of B that we can dissolve into A is going to be here. So a comment from Alexander, our TA. What was it? I guess Alexander's mic's not working, and that was the message of the chat. Oh, there was a question as to what omega represents, right? Omega's not really a physical term. It's just this parameter of the Gibbs free energy of mixing, right? It just tells you how, I mean, not the Gibbs free energy, the enthalpy of mixing is related to the mole fractions, right? So it's just a parameter. right? It's just related to the bond energy and the number of bonds.
Is it so it's dependent on the two materials in there, and is also dependent on the fraction of them?
So
So it's not
omega
constant.
omega is independent of the fraction,
Okay.
right?
But it's dependent on the two materials.
It's dependent on the two materials through the bond energy, through this epsilon term.
Okay. Okay, I see.
Right?
So we'd be given some information calculated.
Yeah, you have to be given some information to calculate it, but it's just a parameter, right? Don't ascribe too much physical meaning to it, right?
Okay.
It just tells you how the change in enthalpy on mixing is going to be related to the composition.
All right. Thanks.
Okay.
I have a question about the last slide, this slide.
Yeah.
So maybe I'm missing something here, but it seems like the way it's written out, a high temperature would actually tend to make delta G positive, which wouldn't that mean it would be less stable?
High temperature is always, you have a negative in the enthalpy term, you got negative T delta S, right? So the delta S is always going to be dependent just on the configurations, the number of configurations, right?
Yes.
And then you have the negative temperature. So as you go up in temperature, you have your Gibbs free energy becomes more negative. So high temperature is going to encourage mixing.
I just don't see that in this equation because it looks like should this supposed to be a minus maybe or something? Because it seems like for this equation, it seems like the temperature gives energy go up.
Okay. Because these natural log terms, right? The natural log of something less than 1 between 0 and 1 is negative.
Oh, okay.
Right? So that's why...
That's what I was confused about.
Right. Yeah, so if you just think about this as delta H minus T delta S. Right?
I understood very well from the reading. I'm just confused for this equation.
Yeah, so but from this equation here, you have to remember that these are mole fractions, so they're less than 1. So these natural log terms have to be negative. Right. Okay, so all is good with the world? Okay. So we can go through the same thing we did for the ideal solution theory and calculate the total free energy of our system, and then we can derive an expression for the chemical potential, and it's got a correction factor here, right? That's got this omega times the mole 1 minus the mole fraction squared, right? Whereas for an ideal solution, we just had this RT ln of the mole fraction here, right? So this is just sort of the derivation of the chemical potential. We don't really need to use it. We can still think about the tangent in the same way. But for an ideal solution, we had this really simple relationship that the chemical potential of A was equal to the Gibbs free energy of pure A plus RT ln of the mole fraction, right? And what we would like to do is make something similar for all solutions, right? This was originally worked out for the regular solution theory, but it applies to all solutions that we're going to talk about. So we can define something called an activity, right? Where we have the chemical potential is equal to the Gibbs free energy of the pure A plus RT natural log of the activity of A. So we're replacing this mole fraction with this modified term activity, okay? And this is purely a mathematical convenience, right? Don't look for any deep meaning. The reading really complicates activity, right? Activity is simply related to the chemical potential, right? There's a neat relationship in optimization theory, right? That says because the natural log is a monotonically increasing function, that the minimum of a function and the minimum of the natural log of that function have to occur at the same place, right? And so because of that nice little relationship, it allows us to substitute the activity for the chemical potential in a lot of cases, right? The activity is just another variable. It doesn't provide any extra information. Both the activity and the chemical potential are measures of the tendency of atom A to leave our solution, right? And depending on what we're doing, the activity can become a convenient proxy for the chemical potential, especially when we're talking about solid state diffusional phase transformations later on, right? So just sort of keep that in mind, right? That we can define, the tangent still gives us our chemical potential, but the distance between here, the free energy of our pure solution and our chemical potential, this distance, right, is minus RT, the natural log of our activity, right? And essentially, this gives us a driving force for mixing. If I put in the amount, if I start with pure A, and I put in the amount of B that gives us our minimum Gibbs free energy, RT ln of A gives me my driving force to form a solution, right? So the activity is related to that. It's also, it says if I'm at my minimum free energy, right? How much do I have to put in energy? Do I have to put work? Do I have to put into my system to separate them out, right? So the activity is really is very important for things like if we're doing trying to develop membranes for, say, filtration and solution separation, right? We need to know the activity of the species that we're trying to get out of water, right? So it really comes in handy quite a lot. Okay, so I
got a question.
Sure. Now that I just closed that. Okay, go ahead and ask.
What is reverse osmosis? Does that have anything to do with potential?
So, well, osmosis is diffusion in a liquid, right? Across a membrane, right? From regions of high concentration to low concentration, right? At least that's the way you learned it in 8th grade chemistry. Reverse osmosis is you put energy in the system to drive things against the concentration gradient, right? So a reverse osmosis filter purifies water, right? By a process that's the opposite of osmosis, right? Yeah, I don't think, yeah, I think that's probably good. This is about Homer. I missed something in the chat. Okay. So if we talk about real solutions, right, we can, the big assumption made in the real regular solution model was that the change in bond energies was small, right? So the number of the deviation from random in the arrangement was also very small. So the number of A-B bonds was very, very close to what you would expect from an ideal solution. Okay? For most alloys and mixtures, this model is really an oversimplification of reality and doesn't predict the correct dependence of our Gibbs free energy of mixing on composition and temperature, right? There is a saying that all physical models are lies that help us see the truth about the world, right? There's another saying that says all models are wrong, but some of them are useful, right? So how do we consider what happens in a real solution, right? We would never, if we just had a regular solution model, we would never form covalent or ionic ceramics, right? And what about polymer solutions, right? Where we have long chains, right? Obviously, if we have large macromolecules, we can't consider the energy of mixing is going to be quite different than simple metal or molecules that have roughly the same radii, right? So, okay. So the assumption of random mixing is at equilibrium is simply not true, right? So the actual arrangement is going to be the one that has the lowest internal energy balanced by the entropy, right? And the entropy term is going to depend on the temperature, right? So it's going to be some potential deviation from this. The actual state is going to be potentially a deviation from the lowest internal energy configuration, right? We know that from thermodynamics. I'm sure you calculated the equilibrium number of vacancies, right, in a crystal, right? That the vacancies all have an energy penalty associated with them, right? It costs you energy to not have a perfect crystal. But you also have the entropy. You have a greater number of configurations in a defected crystal than in a perfect crystal. So it's overall the lowest free energy is what matters. And this gives rise to some really surprising complexity, right? So if epsilon is less than 0, the internal energy of the system is going to be reduced by increasing the number of A-B bonds, giving rise to ordering, right? Which means that essentially AB has a stronger ionic character than AA or BB, right? This implies that there's some electronegativity difference between A and B, right? So if we think about it on the continuum, if a perfectly random metal alloy is completely metallic bonding, as we increase the number of AB bonds and we approach ordering, the ionic character of the bond begins to increase, and we move on the spectrum towards ceramics, right? We can have intermetallic phases that form, or oxides or nitrides in a metal that are ceramics. We could also have metal inclusions in an ionic system, which is more rare, but it does happen, right? If our if our deviation and bond energy, our epsilon term is positive, we get clustering, right? And then we can also get complete phase separation, right? This clustering is really, really important in a lot of systems, right? When we talk about stability of heterogeneous systems starting on Friday and Monday, I'll talk about what are called GP zones in aluminum copper, where you start to form these complex aluminum copper intermetallic inclusions. But first, you get little clusters like this of copper in aluminum, right? And so if we think about this, if the energy difference is large enough that we're going to have a preference of AA and BB over AB, it means that the bond energies and the bond lengths aren't the same. So that means when we have clustering like this, we're going to have different bond stretch between white and black as we do between white and white and black and black. And so that means we're going to have an elastic strain field around all of these clusters. And that elastic strain field can perhaps extend much farther than the size of the cluster itself, right? And when you take mechanical behavior from I forget who's teaching it this term, because Professor Anderson is on sabbatical. You'll learn that the strengthening of metals has a lot to do with the strain field around these small particles. If the size difference is large, then we can end up with an interstitial solid solution, right? So most things that we deal with are going to involve large deviations from our regular solution theory, right? So we can have short range ordering, right? And what the heck do I mean by short range ordering, right? Well, short range ordering is essentially a case that like we see in B, right? These clusters are not arranged on a perfect periodic lattice, right? There is no long range order amongst the clusters, but locally, we see that there is a propensity for AB bonds over AA and BB, right? And we can quantify that with this parameter, right? And this just is just a fraction of how many bonds, different bonds we have, right? So this PAB max, this is if we had a perfectly ordered system with long range order, what is the most number of different bonds that we can fit in, right? So this PAB max corresponds to a figure like this, right? And so it's a difference from random versus the greatest possible deviation from random that you can have, right? And so as this P actual heads to max, we max out this short range order parameter and we tend towards long range order, right? Oops. Yeah. So I thought I had a figure in there. I guess I took it out. Put a figure in. There's a figure in the reading that shows two systems with short range ordering. And by eye, they look pretty similar, right? And I wanted to throw that in there, not because there's any deep meaning, but that just to point out that humans are really, really bad at identifying what random is, right? Actually, on Friday, we'll do a little experiment on that. So, okay, so glass is the ultimate short range order material, right? Locally, we have these tetrahedra, right? Everything is bonded in these silica tetrahedra, right? But the tetrahedra are arranged in such a way, right? They're connected in this network. So locally, no matter where we are, the neighborhood looks about the same. But there is no long-range periodicity to our structure. Right? So in covalent amorphous materials like glasses that we're used to, the short range order dominates, right? It doesn't matter where I'm sitting. My local neighborhood looks the same. But once I go a couple layers out, I can't predict where things are going to be. The further out, the further out I go, the less correlation there is between the structure far away and my point, where I am. But as I come in, my local structure becomes perfectly deterministic, right? Everywhere I look, it's going to be identical. You can have really complicated short range order in systems like metallic glasses, where you get these are nickel, niobium, zirconium metallic glasses, which are potential like catalyst materials. But you can see these complicated icosahedrons that form for the local short range order, right? But the long range packing of these icosahedrons becomes perfectly random, right? But you have these sort of local chunks, right? Long range ordering, right? The reading makes this much, much more complicated than it needs to be, right? So let's just keep it simple and look at the picture, right? If this is the copper gold system, right? So not a particularly useful structural material. But this could have easily been aluminum copper or nickel aluminum or other systems, right? But at high temperature, there is no preference whether this is going to be, whether these FCC lattice sites are going to be copper or gold, right? In the upper limit, close to melting, this is going to be perfectly random. But as we cool down, depending on the composition, there is a strong preference for these layered structures to form, right? And these are called superlattices, and we'll talk about why it's a superlattice on what we mean by superlattice on the next slide, right? But this is a unit cell, right? This has the translational and appropriate rotational symmetry, right? And it for a given composition, right? This is the copper copper gold, and this is the copper 3 gold superlattice structure. Okay. So in the couple minutes that we have left, I want to talk about nickel superalloys. And this word super doesn't come from the fact that we form a superlattice. But I want to make a bold statement, right, that says that other than silicon, which enabled electronic devices and computers, right, the nickel-based superalloys have done more to enable modern life than any other material, right? And why do I say that? and I'm going to make the argument because nickel-based super alloys enabled cheap air travel, right? Why do they enable cheap air travel? Because they allow, these are the metals, the materials that are in the hot section of a turbine engine, right? And the better that these materials have gotten, the higher the operating temperature and the thermodynamic efficiency of jet engines has gotten, meaning we have to burn a lot less fuel, right? So it's estimated that if you can raise the operating temperature of a jet engine by 50 degrees, that is $1 billion a year fuel savings across the fleet of those aircraft compared to the previous generation. That's a lot of dinosaur juice that's being saved, right? And it also means that we have cheap air travel, right? Even when I was a kid, right, which wasn't all that long ago, air travel was a really expensive endeavor, right? People still dressed up in suits and ties to get on an airplane. The cost of a transatlantic flight in actual dollars hasn't changed, right? I mean, not in actual dollars, like it still cost $1,000 to fly one way across the ocean, right, in the 70s. But $1,000 was a lot more money back then, right? So in terms of real current day dollars, air travel was much, much more expensive, right? If you think about it, is there anyone in this class that has never been on an airplane? Right? If we asked that 40 years ago, that was not really the case, right? You know, it used to be that if you went to a different country, you moved to a different country, that meant that perhaps you might never see your family again because the sheer cost of going back, especially with a family, right? My mother came from Italy in the 60s, and it
The
wasn't
only thing I can really think
until
of is
she
this
was really
stupid
a grown woman that she went back.
pen guns we used to make in elementary school with like 3 springs to make them stronger. Do you remember that?
I'm not sure. Hold on, let me. Okay. So I thought that was a question. I try and leave things unmuted so that people can interject. But okay, so that's my argument, right? The fact that by enabling cheap travel, nickel super alloys have changed the world really dramatically. Okay. And part of this revolution has come, the cool thing about super alloys is these blades are actually single crystals. They're cast structures that form a single crystal. And the reason why these work is it's a two-phase mixture. We have an FCC structure, which is the gamma phase. And then this window here is nickel 3 aluminide, or this gamma prime ordered structure, right? Where we have nickel on the face sites and aluminum on the corner sites, right? And this is called the L12 crystal structure, okay? So what's the composition of this, right? Well, we have each one of these corner sites contributes what? 1/8 right? So we have 1 aluminum atom per unit cell, and then each face site is half. 1/2 times 6 is 3. So this is 3 nickel atoms, 1 aluminum atom per unit cell. And what's the crystal structure of this? It's not FCC, right? Because the face sites and the corner sites are not identical. Right? What's the crystal structure? Anyone have any idea? Right? We can think of this actually as a simple cubic crystal, right? Where our lattice points are the corners. And our motif at each lattice point is 1 aluminum atom plus 3 nickel atoms, right? And that motif is endlessly repeated at each corner. So this L12 lattice can really be thought of as a simple cubic crystal, right? And it's called essentially a superlattice because we have 2 interpenetrating crystalline lattices, right? We can think about this in many different ways. We can think about this as 2 interpenetrating simple cubic lattices as well. So the superlattice idea comes because is really interesting because what's going to happen if the dislocation comes through? We're going to move a aluminum atom onto a nickel site and a nickel atom onto an aluminum site. So deformation of this also incurs an energy penalty because now we have misplaced atoms, right? So I'm out of time. I will just wrap this up really fast on Friday, and then we'll talk about the heterogeneity of the equilibrium in heterogeneous systems and the stability of heterogeneous systems Friday and Monday. Look for the homework, and there'll be another reading assignment posted as well. Okay, take care, everyone. Have a good day.